So last time, I told you about, the experimental verification of, the Bose-Einstein condensation. That happened in 1995. There were two groups, one in Boulder, Colorado, another one in MIT, and there was a Nobel Prize given for that in 2001. And what these groups essentially did is that they took like some atoms which were bosons, and they were rubidium or sodium, and what was the other thing? Lithium. So lithium. So, and then what they did, that they took about 10,000 to about 10 million of these guys, and then they cooled it down to cooled it down to unimaginably low temperature, like 10 to the power minus 7 K. In contrast, the temperature of the cosmic microwave background is about 2.7 Kelvin. So if you don't know about the cosmic microwave background, it's essentially, a black body radiation, which you should now know. So, and a black body radiation has this maxima, if you remember. So you can, associate the temperature. I'm sorry. You can associate the temperature associated to the maxima to the radiation, and that's how we calculate the 2.7 degree Kelvin. So you cool down this gas even below the vacuum of outer space, and then what happens is you trap it in a magnetic trap. So there's a magnetic trap, and then you release it from the magnetic trap and you observe it after it travels for a little distance. And then did I show you the pictures last time? Yeah, I did. So, and then what happens is that, let me just show it to you again. It's such a nice picture. So after a little, they've traveled a little distance, these create smudges, and, these are, more or less the same size. And so this guy is at a temperature above TC, the critical temperature, and this is around the critical temperature, and this is well below the critical temperature. And what they observe is that, this is the physical space picture, but because you now know you have a snapshot in time, so you can calculate the momentum, and if you compute the momentum distribution, this is what it looks like. And because these are free particles, the momentum is a measure of its energy and therefore its state. So we see that there's a bit of a distribution. It's a Gaussian distribution. And here at t equals to Tc, we get something which is very, very sharply peaked. And at below Tc, we get extremely sharply peaked. That means that most of the particles have the same energy. Okay, so this is the experimental verification for which, they got the Nobel Prize. So, Okay, so this is not it. Okay. All right, any questions?